Hi there, students. So in this note set, we're going to take a look at a way of describing electrons that are possessed by an atom in a little bit more detail than what we've covered so far. First, let's review what we already know. Through advancements in chemistry in the early 20th century, we know that electrons are negatively charged subatomic particles that exist in a cloud somewhere around the nucleus. We know that we can't pinpoint the location of an electron. Rather, we know that electrons, like light, have both particle-like and wave-like properties, which is why the Bohr model diagram wasn't entirely wrong, and the quantum mechanical model, which incorporated the wave-like properties of electrons in describing them, was an enhancement, really, of the Bohr model. It didn't replace it, it just enhanced it. We know that the regions of space where we're likely to find electrons are called orbitals. And the solutions to Schrodinger's wave function, which is very high level math, results in some funny looking shapes. We know from Max Planck that electrons and the electrons that inhabit the atoms absorb and give off energy only at specific wavelengths, not just any wavelength of light or electromagnetic radiation, but specific ones that correspond to the differences in energy between electron energy levels that are found within that atom. And lastly, we know that the electron is the most important subatomic particle. It's the one that determines how an atom behaves and reacts with other atoms. You might think, oh, geez, a proton is so much bigger than an electron and it determines the identity of the element. Well, that's true, but the proton is not the subatomic particle that reacts. Really, students, chemistry is all about electrons. And that's what we're going to dive into today. In this note set, we're going to describe in greater detail the electrons that an atom possesses. And when we get to part 2 of the note set on electron configurations, we're going to see why the periodic table has its really funny shape. I'm sure you recognize this shape. We see it all the time in chemistry. But why is that shape not a perfect rectangle or a perfect square even? Why does it have this particular shape? That will become clear by the end of our notes on electron configuration. Okay. Now, an atom possesses electrons in energy levels. We've used the term energy levels, but some scientists use the term electron shells, or even energy shells if you prefer. Every principal energy level, or shell, has sublevels within it, also known as subshells within it. Those subshells have names. S for S-type orbitals, P for P-type orbitals, D for D-type orbitals, and there's even F for F-type orbitals. And if you get to really big atoms or even atoms that are excited beyond ground state, you could have G for G-type orbitals. But students, the atoms that we're going to consider will only occupy S sublevels, P sublevels, D, and F. And it always goes in that order. S, then P, then D, then F. One way to remember that is St. Patrick's Day Fun, SPDF. Each of those sub-levels or sub-shells has orbitals within it. There's one s orbital. There's 3 p orbitals. There's, if you count the boxes here, 1, 2, 3, 4, 5 d orbitals, there's 1, 2, 3, 4, 5, 6, 7 f orbitals. So every sublevel has orbitals within it. The number of orbitals within it is unique to each type of sublevel. And then, if we even break that down one step further, every orbital can hold or house up to 2 electrons. We'll see why in just a moment. Okay, so let's recap. The number of sublevels that exists within a given principal energy level is equal to the number of the principal energy level. We name the sublevels for the types of orbitals that are found in them. So an s sublevel will contain s orbitals. A p sublevel will contain p orbitals. A d sublevel will contain d orbitals. And an f sublevel will contain f orbitals, etc., because there really is no limit theoretically to the kinds and numbers of sublevels. So let's make a little chart here. We're going to list the principal energy level, the number of sublevels that exist within that principal energy level, and then we're going to name the sublevels. In the first principal energy level, there is one sublevel. Notice that the number of sublevels that exists is equal to the numerical value of the principal energy level. And since there's one sublevel that can exist, and we always start with the S sublevel, we name that sublevel the 1S sublevel. In the second principal energy level, there are 2 sublevels that exist. Notice the number of sublevels equals the numerical value of the principal energy level, and they have names 2S and 2P. Always going in order, S, then P, then D, then F. St. Patrick's Day fun. In the third principal energy level, there are 3 sublevels whose names are 3S, 3P, and 3D. There is no such thing as a 3F sublevel. It doesn't exist. And in the fourth principal energy level, there are 4 sublevels whose names are 4S, 4P, 4D, and 4F. Going beyond that, students, you don't need to know. Yes, there will be elements that go beyond the 4F sublevel. We might address some of that in our next note set, but for right now, this is all you need to know. Okay. Every sublevel has orbitals within it. Let's list the sublevel, the number of orbitals found in it, and in some cases, we'll name them. Okay? So for all of the S sublevels, whether it's the 1S or the 2S or the 3S or the 4S sublevel, all of them have just one orbital in that sublevel, and they're all named simply S orbitals. For the p-type sublevels, there are 3 orbitals whose names are p subscript x, that means the px orbital, the py orbital, and the pz orbital. For D and for F, I'm not going to ask you to worry about the names or even the shapes of those sublevels. Remember, orbitals are mathematical solutions to Schrodinger's wave function, and it gets really complicated. The shapes are kind of goofy, and beyond just knowing S and P, I don't need you to worry about it. So don't worry about D sublevel names or shapes, but I do want you to know that in a D sublevel, there are 5 orbitals. In an F sublevel, there are 7 orbitals, and again, don't worry about shapes. Hey, look at the pattern. If you count by odd numbers here, 1, 3, 5, 7. If we had G sublevels, it would be the next odd number, 9, number of orbitals in it. Hey, there it is. G sublevel, 9 orbitals. It goes by the odd numbers. I want you to remember that s orbitals have spherical shapes. P orbitals have dumbbell shapes. And the dumbbells are oriented along one of the three axes in three-dimensional space. Remember, we're considering three-dimensional shapes. So we're not just talking about a Cartesian plane with an X and a Y axis. We want you to put together X, Y, and Z. So the P subscript X orbital is oriented along the X axis. The PY orbital is oriented along the Y axis. And the PZ orbital is oriented along the Z axis. Here's a way to visualize that. A drawing, an artistic rendering of those shapes of orbitals, spheres for the s orbitals, dumbbells for the p orbitals, and the dumbbells are oriented along each of the three axes in three-dimensional space. Do not worry about the d orbitals, which have cloverleaf shapes, most of them, and the f orbitals. But do notice in this chart, it lists the number of orbitals per sublevel, 1 for the s sublevel, 3 for P, 5 for D, 7 for F. Okay, one last bit before we get down to electron configurations. This deals with what's called the Pauli exclusion principle. Pauli was a scientist who discovered this. He says, in an orbital, you can hold up to 2 electrons, but, and this may seem weird without physics background, but since electrons are moving negatively charged particles, they generate their own magnetic fields. And so to house the 2 electrons within a given orbital, they have to be spinning in opposite directions. Take a look at this picture. If, let's say, electron A is spinning clockwise, it generates its own magnetic field with a north pole and a south pole. But to have another electron in that same orbital, it has to be spinning counterclockwise so that the north and south poles face each other. You can't have 2 north poles face each other. For us students, if you can just remember that every orbital holds 2 electrons, we'll be fine. But I wanted to give you a little bit of background about why that's the case. Okay, let's summarize what we've covered so far. It's a lot of goofy stuff. Sometimes one complete chart will help to simplify things. So don't freak out when you see this at first. We're going to take a look at each of these columns and rows together. The leftmost column lists the principal energy level, which we abbreviate N. Remember from the Bohr model of the atom, N equals 1 is the first ring around the nucleus, and N equals 2 is the second ring. This is the same thing. Within the principal energy level, there are sublevels whose names we've listed here. And within the sublevel, there's a certain number of orbitals that's characteristic of the type of sublevel. Then we can list the number of orbitals in the entire energy level, which, as you'll note, is always equal to the principal energy level number squared, N squared. Principal energy level is N. The number of orbitals it can hold is N squared. And then lastly, if we know Pauli exclusion principle, the number of electrons that can be held in that principal energy level would be 2 times N squared. So let's go through this. First, principal energy level has only one sublevel. It's called the 1s. The number of orbitals in any s sublevel is simply 1, which means in this entire principal energy level, there is but 1 orbital which can hold 2 electrons. But in the second principal energy level, we have the 2s sublevel and the 2p sublevel. The number of orbitals found is respectively 1 and 3, which in the second principal energy level, that makes 4 orbitals in total, which if you multiply by 2 gives you 8. Third principal energy level, 3 sublevels, 3s, 3p, and 3d, with number of orbitals 1, 3, and 5, which add up to 9 orbitals in total, giving you 18 electrons. The fourth principal energy level has 4 sublevels, 4s, 4p, 4d, and 4f, which gives you a total number of orbitals So all of that is nice to know, but how is that going to help us describe the arrangement of electrons in atoms? In comes the electron configuration. An electron configuration is simply the way a chemist describes where electrons within an atom are found. When we write electron configurations, at least for now, we're going to make two major assumptions. Number one, atoms are neutral. And what that means for us is, however many protons there are in the atom, there's also that same number of electrons. The positive charge cancels out the negative charge, making the atom neutral. Secondly, electrons are in ground state configuration. That means we are not going to assume that any of the electrons are promoted from one energy level to another. We're going to picture them as close to the nucleus as possible, since normally electrons being negatively charged would be attracted to the nucleus, which is positively charged, and they would want to get as close to that positive charge as they could. When writing electron configurations, there's a little trick to the formatting. Let's take a look at this. Let's take hydrogen. Hydrogen, the simplest of the elements, has just one proton in it, which means if it's neutral, it'll have just one electron. In our format for electron configuration, we're going to list the sublevel that it's found, and of course the name of the sublevel contains the principal energy level number in it. Then it lists the type of sublevel or orbital type. If it's starting with S, then that means 1s. And then we're going to write a superscript, small text to the upper right of the letter, which lists the number of electrons within that orbital. It is not a mathematical superscript. It's not like an exponent at all, which is kind of unfortunate. I wish it wasn't listed as a superscript, but it does, since we use subscripts elsewhere in chemistry, like when writing chemical formulas. I think chemists said, well, we need a small number and we need it not to look like a subscript, so hence the superscript. Let me give you an example of a rather long electron configuration, not something you won't be able to handle in a couple of days, but here's iron. Iron has an atomic number of 26. So if it's neutral, it would have 26 electrons. And you might say, gee whiz, this is a lot to write. You're correct about that. There is a shortcut that we'll learn tomorrow or the next time we have a note set. The electron shell, or principal energy level, is listed first. Then the sublevel, or subshell, S, and the number of electrons that can fit within it, 2. After that sublevel is filled, we move on to the next one with the next higher energy, the 2s sublevel, which also can hold 2 electrons. Remember, S-type sublevels only have one orbital, and each orbital can hold 2 electrons, which gives you a maximum holding capacity of 2. But after the 2s sublevel comes the 2p sublevel, which contains 3 orbitals, and if you can hold 2 electrons per orbital, that gives you a maximum capacity of 6. After the 2p sublevel comes the 3s, which can hold 2, the 3p, which can hold 6, and then something goofy is going on here with the 4s and the 3d, and we'll address that next time. I do want you to notice, if you add up all of the superscripts, 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 6, it's a lot of 2s and 6s there, but it would add up to 26. And that is the atomic number of iron. Because it's a neutral atom, we would assume the same number of electrons as protons. And secondly, when you see superscripts in electron configurations written out, they have no mathematical meaning. They don't mean anything mathematically, no squares. It's not like we're taking p to the 6th power or anything like that. Okay, let's try a worked out example and then 2 sample problems, and we'll turn you loose on your homework. Let's say that you were asked to write the electron configuration for aluminum. The first thing we would want to do is find aluminum on a periodic table. Go ahead and find a periodic table, either paper or electronic, and go ahead and pause the video here to do that. But you will need a periodic table to refer to very frequently from here on to the end of the year. So it's best to have one easily available. When we look up and find aluminum, you'll see a box with a whole number 13, the chemical symbol Al. If you're lucky, the periodic table will write out the name of the element as well. And you'll see a goofy decimal, 26.98, which would tell you the average atomic mass. Since the atomic number is 13, we know that the number of protons is 13. If it's a neutral atom, and that's going to be our assumption going forward, then we'll have the same number of electrons as protons, so we will also have 13 electrons. Let's write the sublevels in order from lowest energy to highest. It would go in this order: the 1s, followed by the 2s, followed by the 2p. This should say, one second here, this should say 2p sublevel. Then the 3s, and then the 3p. But we're not going to need to go that far, actually. Let's consider how many electrons can fit in each of those sublevels. S sublevels, because they only hold one orbital in them, can only have up to 2 electrons. P sublevels have 3 orbitals in them, which means they can hold up to 3 times 2, that's 6 electrons. We need to find a home for all 13 electrons of aluminum. And in that case, that works out to be 1s2, 2s2, that means 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, 6 electrons in the 2p orbitals, 2 electrons in the 3s orbitals, and then if you count what we have so far, 2 plus 2 plus 6 plus 2, that's 12. We only need 1 more electron to find a home. That last orbital finds its home in the 3p orbitals. Yes, the capacity of that 3p sublevel would be 6, but in this case, we don't have another 6 electrons, we only have 1 more. So the electron configuration ends with 3p1. Let's try another example. Let's say you're asked to write the electron configuration for carbon. Assume the atom is neutral and in ground state configuration. When you go to find carbon on the periodic table, you'll see a box like this, chemical symbol C. If you're lucky, you'll see the element's name written out. You'll see a whole number 6 and a goofy decimal. The goofy decimal doesn't have any relevance to us right now, but that whole number 6 does. That tells us there are 6 protons in carbon, which, if it's a neutral carbon atom, means that there will be 6 electrons in it. We need to find a home for 6 electrons. The order of the sublevels as they fill will go from lowest energy to highest. Well, if we've got to find a home for 6 electrons, the configuration looks like this. 2 electrons find a home in the 1s sublevel. The next 2 electrons find a home in the 2s sublevel. And then we've got to break into the 2p sublevel as well. And even though the capacity for that 2p sublevel would be 6 electrons, we don't have another 6 electrons. We only have 2 more electrons. So the configuration for carbon ends with 2p2. One last example. Let's say we're asked to find the electron configuration for sulfur. If you look up sulfur on the periodic table, you'd see atomic number 16. The whole number in the box is 16, which means both the number of protons is 16, and if it's a neutral atom, the number of electrons is 16. check out this electron configuration. The first 2 of the 16 electrons find a home in the 1s orbital. The next 2 find a home in the 2s sublevel. The next 6 find a home in the 2p sublevel. The next 2 in the 3s sublevel. And then, even though the capacity of the next sublevel is 6, we only have 4 more electrons, which means our configuration ends with 3p4. I invite you to try your homework now, where I'm going to ask you to write configurations for the first 18 elements.